All right, good morning again, class. We want to continue kind of with where we left off. Now, one thing I will say this Friday, be prepared. I'm probably have to do a Zoom class again. My appointments last week got messed up, so they're in the middle of my class now Friday. So just kind of keep an eye out. If I can get it changed, I will do my best to do that. If not, just know from today, Friday's class will probably be Zoom again. Okay. Moving with the stuff that we've been talking about, the other thing I want to remind you is limits. I'm using limits. Hopefully you got a good idea of what we're looking at from Friday. If you weren't there for the lesson, make sure you look at the recording. But Friday's talking about limits that I try to do an overview of the different ways we can use them. That isn't the main focus of our course though. So yes, there's some homework assignments that focus on limits. So if you get stuck on something, you need to reach out to me, right? Use my office hours right before our class starts on Monday, Wednesday, Friday to go over that. I can help you better understand, okay? What I hope to do today, though, is kind of start building the bridge of why are limits important for us and what does it help me get to, okay? With that said, one important thing from limits that you should take from Friday was continuity. That's definitely something that I know I kind of briefly mentioned, but we'll have to talk about like, yeah, that is important for the math to work moving forward, okay? But please hear me out. It's not the main focus of our course, okay? With that said, when I look at limits, the one thing I want you to see here with this one is remember, we're not actually just plugging in the points. So we're not going to the ordered pair and like, what's the ordered pair? It's not what a limit does. We can evaluate a function as we learned in college algebra, plug in the next value, work it out. We can do that. What happens is with a limit, remember, we're using the information around to understand what's going on, okay? So what does the limit as x approaches -1 of f of x give us? What did someone put? Are we on agreement with 6? Okay. Now, the nice thing about this one, I gave you the function, right? So through direct substitution, you could have found that, hey, it works fine here, right? Just be careful for those situations, though, where we have where we can evaluate the limit, but we can't actually plug in a point, right? Remember, the hole in the graph was an example I gave last week. Okay, there are other kinds of discontinuity, right? I talked about asymptotes, I talked about holes in the graph, but also know that we had that where the function was broken up because of a piecewise function, okay? Is there any concerns with limits kind of from this perspective I could help with? All right. The next thing that we need to look at is the rates of change, okay? So what I did here is I took the same graph, right? And I picked 3 different points, okay? What we want to look at though is we're going to say, hey, going from this bottom point, what's the average rate of change going up to the high point up here on the right? And then the second pair that I did was the bottom point to this lower point on the right, okay? Now, the average rate of change, though, what we're saying is, hey, what's going on with my graph as I go from left to right to get to that next point? Okay, so both of these situations, we should expect a positive rate of change because it's going up, right? If you remember from college algebra, that was where, hey, the graph is increasing or decreasing was kind of what we did. We talked about average rate of change. We did it a little bit. And then we talked about how it's increasing or decreasing. We can now put more mathematical ways of describing that now, right? With the limit in place, especially, we can start bridging to that, okay? What is the formula for the average rate of change, though? Anybody remember that? If I said
the second y minus the first y.
Yeah, that's our average rate of change, okay? That's how we find average rate change. We need 2 points to do so, right? Once we have 2 points, we plug in the points to find the change in y value and the change in x value. The rate of change, though, is saying that, hey, I'm working with something that's got 2 dimensions, right? Now, the part that we have to remember is we're always going to put the rise over the run on this. The change in y over the change in x is a great way to put that, right? Your textbook and some of the videos you'll see, the triangle is going to be more used in this course than just words, okay? What you're going to find here as we move forward, once we put the limit with this, we're going to be able to get to what we're going to talk about is differentiation. Okay, that's going to be the step that we're moving towards here, where we'll have some rules that we can use to help us find things like the average rate of change, but ultimately we want to get to the instantaneous rate of change, right? What's going on at a particular moment, not just over a time period, but a particular moment, okay? Now for this problem though, we are looking at the average. Now make sure you see though, as we said, we want to make sure we're getting positive values for our rate of change here. Okay. So for that first one, we have what? 6 minus -2 all over, I said 5 minus 3. We good with where I'm getting those values from? Okay, so what were my x values for the first one I said? 3 and 7, right? So make sure you see here we have, what is going on? I'm sorry, y'all. Those ordered pairs at x equal to 3 and x equal to 7. Okay, so all we needed though was the y value. So we're going to take that and look to our y value. Okay. Now, again, you could have taken the function too, though, right? Plugged in the x value to get the y value. But I put the graph there to, so we could have the visual representation of how the average rate of change should be positive. Okay, that's where I wanted to start from a visual approach. Okay. With that said, though, that gives us what? 8/2 or a +4. Okay. So it changes pretty quickly. But the key is it's positive. That was the, hey, it's going upwards, right? We're seeing an increasing pattern between these 2 points. All right. Now, the next one, we should expect positive though. But when you look at this average rate of change that we just found, and this second average rate of change should be positive still, but should be bigger or smaller than 4? What y'all think? Let's find out, right? So this one here, we should have 0 minus the -2 all over the 5. Uh-oh, y'all. I messed up. I'm sorry. This first one should have been 7 minus 3, y'all. I was supposed to do 7 with the first one, okay? So that would give us 8/4, which is 2 instead of 4. Still positive, but it should be 2 instead of 4. My bad. Now, with that said, the second one should have the 5, not the first one. Okay. I had the y value correct, but I used the wrong x value there. Sorry. But that would give us 5 minus the 3. So this will give us what? 2/2, which is equal to 1. So it's positive, but it was smaller because it's not as steep, right? Another way you could describe that would be angles, right? So if you chose to take trig, we could go in there and talk about how the different angles there. Okay. Are we good though with, once I correct my mistake here using the wrong x value, we go with the average rate of change over just plugging in the point and getting it? Now keep in mind, I gave the graph, that was a great representation, but if I gave you the function, just know you have to plug it in to go find the points, okay? Now, so let's look at another one. All right, here's another function. 2 different average rates of change that we want to look at. This time though, we're going to be forced to plug in, okay? With that said though, what variable does the 2 and the -3 represent when we use function notation again? So when we write f of 2, the 2 is our x value, right? So make sure you're seeing here, this is x equal to 2 and x equals to -3. Okay, the function notation is just a nice convenient way to write that, okay? But know that here is, again, I have to go find the y value. Okay, the reason that we like to use the x value first though is because remember, x is our independent variable. I could plug it in and use the order of operations to simplify, and I'll have my y value because y is already solved for. Okay. With that in place, right, what do you get when you plug in 2 here? All right, so what, everyone agree with 4 minus 3 equal to 1? And then f of -3 gives us what? -6 minus 3? We all good there? Now we have our x values and our y values, so we can go do the same thing we did before. Now, does it matter the order we put these points in? Which one's 0.2, which one's 0.1? Let's find out. That's the order I gave them, right? I said do f of 2 first and then f of -3. So I'll follow that first. So -9 minus the 1 from the y values that we just calculated. And then -3 minus 2 get using the x values we're given. So it gives what, -10 all over -5? Or a +2. Okay. Now, like I said, let's just check it the other way. 1 minus -9 all over 2 minus -3. What you find there, you just get +10 and +5. Both signs change. So just keep in mind, if you get stuck, remember the key here is that the ordered pairs better be on top of each other. That's one thing to kind of watch for. Okay. Now, were you surprised that we got a 2 there? What type of function did I give us? It's linear, right? It's a line. Okay. Remember, whenever you have a line that's in that mx plus b form, what does the m stand for? All right. The m is our slope, right? We're going to kind of build towards this why do we call it the slope, right? Now, if you remember from your college algebra class, though, when we look at the average rate of change of any points, we're going to get 2. Okay. So let's try that out with 5 and 5 plus h just to see what happens. Okay. Shrink this a little bit. By the way, for those of you who came in after I took roll, make sure you see me after class so I can get that fixed. All right, for this problem, f of 5 gives us what, 10 minus 3? So we get 7. What you're going to find here, though, with the second one, all we're going to be able to do is simplify because of that h. So just keep in mind the h, all I can do is simplify, but let's simplify as much as we can. We're okay with where I'm getting the 2h and the 7 from? Now keep in mind, as you saw with the first pair, we didn't have to do that, but as we move forward, we should expect something with the plus h kind of occurring a bit more often, okay? As we build through the next problem, you're going to see that it definitely has an important part of what we need. What you're seeing here is our first point is 5. 5 plus h is saying any points, h from 5, okay? So that's why we like that. But as I go do the average rate of changes we saw here, my second point is going to be 2h plus 7 minus 7 all over 5 plus h minus 5. Okay. So keep in mind, that was our second x value, and that was the second y value that we found when we plugged it in. Okay. The nice thing about that is, hey, the 7s and the 5s cancel out with one another to 0, right? So that gives us 2h all over h. And what happens next? That's nice. And the h is divided out, right? Giving us just 2. Which is nice, right? Because what we see is that consistency, as we just talked about. Hey, I'm working with a line, and a line, right? When we have a linear function, it has a constant slope. It does not matter what 2 points we pick, right? The average rate of change will always be 2. That's what makes it a line. Okay, now this one is 2, right? Because that's what I picked. Now, what we need, though, is to build a more mathematical way to describe that, because that h kind of just disappeared, and that's not always going to happen. So this is where the next step comes into this process. So keep in mind, the average rate of change is just, hey, what's going on between 2 points on a graph? With this, hey, we had a positive change no matter what 2 points I picked, okay? The difference quotient, though, some of you might be remembering one of your favorite things from college algebra, is the step that we need in the right direction, okay? What you're going to see here, though, is we need to combine this with limits, all right? As I mentioned, the average rate of change is great. But sometimes we would prefer to know the instantaneous rate of change, right? The instantaneous rate of change might be more valuable for us for something than the average rate of change, right? So we're trying to make that step forward. Okay. The difference quotient allows us to do that. So the difference quotient takes kind of what we looked at just now. It says f of x plus h minus f of x all over h. Now, if you think about the x values we just plugged in though, x plus h minus x, as we just saw, these x's go away, right? So that's why it's just h in the denominator. So keep that in mind. It's the same thing we just did, but instead of 5, I'm keeping it general. Let's just use x. Let's not be specific, keep it as x, okay? Now with that said, what should I get from this function right now as we do this? What did we just learn from this one here? What is my average rate of change going to give me? So what should it change if I change the x value? Well, it shouldn't matter, right? So let's see if that's true. Now, it's not always going to be the case, right? So I got another function after this where we can kind of compare and see the differences, right? But I felt for the simplification aspect, linears definitely help with that. And then knowing the slope helps with that confidence as well, okay? With that said, though, if I go through here, the one thing I do not have is that f of x plus h. But keep in mind, once I plug that in, all I can do is distribute the 2 as we saw before. The big difference here is I'm left with 2x plus 2h minus 3. I can't combine anything. Okay, so make sure you go back to the work that we did here. But know that we can't combine terms like we did before. So that's why I'm just leaving it as 2x and 2h. Okay. With that said, though, now we can plug in the information we needed. The one thing I will say here is be careful with your parentheses. Right? As we saw kind of on some of the previous problems, I was mainly using parentheses for like negative numbers. But as we move forward, we're going to be dealing with expressions. So we have to be careful to show that like, hey, 2x minus 3 was the entire function that I want to subtract here. This is very important because we don't want to subtract one term from a function. We want to subtract everything in that function. So when I get to this next step, we need to make sure to say, hey, I got to distribute that negative to both terms. Okay, that's one thing I would say as you guys deal with some of these, especially on the homework and preparing for that first test, be careful. And what I plan on is like the test wise, like I said, limits are important. So it might only be like one of these problems on that test. Keep that in mind. There will be some limit problems, but what we're moving into for differentiation is going to be kind of the focus of setting everything up. So please keep that in mind as I do this. With that said, though, the numerator gives us 2x plus 2h minus 3 minus 2x plus 3 all over h. A little bit more going on, but what's nice about what we have now? Yeah, right. The 2x is opposite signs, right? The 3's, opposite signs, gone. And look at that. Isn't this kind of what we had before in a similar way? 2h all over h, which gives us just 2. Right? As I mentioned, we did the same thing with 5 and 5 plus h, right? With a line, what we see here, the slope is constant no matter what values I pick, okay? Now, the way that we incorporate the limit then is we say, hey, when I deal with this, we should write this as, oops, the limit of this thing as h approaches 0, okay? Now, why would we want to say h approaching 0? Well, focus on this piece here. If h was 0, what would that equal? What's x plus 0? It's x, right? A number plus 0 is itself, right? With that said, then wouldn't those two things be exactly the same? Now, the problem is the reason we can't technically do what we just did. What would that mean? If that became 0, there'd be a 0 in the denominator. Now, what happened is through our simplification, we got away with some stuff, right? Because the h is divided out. I didn't even have to worry about it. But understand, when we're doing this work from the beginning, one thing that we have to remember is like H cannot be 0. Okay, so the limit helps us work through something that we didn't really have the ability to do before. Simplification gave us a good way to work around something, but now we have a way to deal with it. Okay. Now, with that said, though, if we go through all our work down here and you have the limit as H approaches 0 of just 2, well, the H simplified out, right? So what's the limit going to equal? The limit of any constant term is going to be that constant value. That's a nice thing about it, right? Since the H is divided out, hey, it does make the limit nice. It is too. Okay. But the limit gives us a way to better put a box around what we're dealing with from a mathematical standpoint, right? So keep that in mind. From the mathematics side of things, we now have a way to say, yeah, we have confidence that this represents the average rate of change between any 2 points. And now we're stepping into that realm of instantaneous rate of change from a mathematics standpoint, okay? With that said, does it change completely when I do a different function? As y'all writing this down, what type of function do we have? Quadratic, right? So what shape does that give us when we graph it? Like you are a parabola shape, right? Well, one side's going to have an increase, right? One side's going to have a decrease, right? But those are not consistent from point to point, right? The average rate of change is always changing depending on the points we pick. The one thing that is consistent, one side is positive, one side is negative. You could also talk about symmetry, right? So if you look at the left and right side, if I go take the points that I just did on this problem to begin with, and I said, hey, let's pick instead of the 2 points we did here, right? If I did these 2 points, I should expect the same value, but the opposite sign, right? So there is symmetry involved, but as you saw just between those two, we definitely got different values back, right? So it's not a constant rate of change. It's now variable, right? This is where we're going to start to see how we can determine the rate of change based on the function we have. Now, with that said, though, one thing we do have to remember is the difference quotient, right? So we need to make sure to say, hey, this is going to be x plus h, and the other one's going to be just my function. The key is that's 2 y values, and we're just trying to subtract them, okay? Now, with that, you just declared your x values. So if you ever get stuck, just remember x plus h, and then go over off to the side, what's x plus h minus x, because that would remind you, hey, the denominator is just h, okay? It's still the rate of change is where we're getting this from, y2 minus y1, all over x2 minus x1. It's not something new, it's just, it's in function notation now rather than general ordered pair form, okay? Now, the part that does get a little bit involved, and you're going to find, especially on a couple of the problems on the homework, it's going to be simplifying this thing. Okay, so that's why it's like, hey, it's good. I'll make sure I have one on the test as reasonable, right? Make sure we can simplify it and we focus on the limit. But please understand, this can get really messy depending on what we're working with. Okay, especially if I throw some like exponential or logarithm stuff at you, simplifying it's definitely going to involve more than we want to spend time on. Okay, so keep that in mind. But here we definitely have the ability to deal with this. We just need to go in and say, hey, what is g of x plus h? Okay, well, it's this wonderful expression. Now, kind of following what we saw before, we definitely want to simplify because we're going to expect some terms to combine to 0, right? And drop out because they're 0. With that said, how do we multiply this first one again? All right, we need to write it twice and do the distribution, right? Foiling is a great way to remember that, okay? I think someone said they'd like to do the box method. That's great as well. All right, when you do that, though, make sure you go confirm on your own time that this will give you x squared plus 2xh plus h squared. Okay, the key there is go confirm that that should be 2xh in the middle, okay? If you don't FOIL, you probably won't have that. So that's why it's important. If you get stuck, write it twice and do the multiplication. The good news is anytime you see x plus h squared, it's always going to be that trinomial. Okay, that's the nice thing about that. Distributing the -3, watch your signs, as we mentioned before. And don't forget your -10. Okay. One thing I will say with these, always double check, hey, did I handle my signs correctly? Did I accidentally drop a term somewhere? Because as we go through this, we should expect a lot of stuff to drop out. What variable should we be watching right now as we go through this process? H, right? Keep in mind, as we talk about, the limit as H approaches 0, it's going to be something we add in a second to kind of show how it all comes together. Okay. Now, with that in place, then I can go do my difference quotient now, because I have g of x plus h. Oops. Technically speaking, you could put both the first expression and the second expression in parentheses, but I usually just do the second one because that's the one. It's like, hey, don't forget to distribute the negative. Okay. All right. So does that work out nicely like we expected it to just now? Oops. Yep. See, even I forget stuff, right? Hopefully you caught on to that. I'm not perfect, right? I meant what in the video I went and started counting the wrong way at one point. So those negatives, it's easy to forget. Okay. Now the guys mentioned, I think I heard someone was saying is, hey, a bunch of stuff about to cancel out, and you should expect that. The key is remember, all that I should have left on terms right now, the only terms that should be left is any term that has h involved. Okay. So as I go through here, my x squared's gone. The 3x's are gone. And once I put the correct sign on that 10, that's gone too. Right. With that, though, that gives us something definitely a little bit nicer to work with. 2xh plus h squared minus 3h all over h. And we like that because what does every term in the numerator have? H. And how many can I divide out now? Right. So if you need to, remember, just break it up by individual fractions. You don't have to write this way, though. Please understand that. Just remember that since every term has h and I'm dividing by h, I can take one h away from every term. Okay. So at that point, we just found the average rate of change between any 2 points, right? Specifically a point and a second point that's h away from it. The big difference here is we saw at the linear, we just got our slope back because it's a constant rate of change. This time my result, though, happens to be a function of its own, right? It has both x and h left over. Okay. And this transition is a great place to see why we need the limit, right? Before the linear, we dealt with slope, right? You probably are like, okay, we got the slope down, slope formula. It's the same between all points, but here we're seeing, hey, I can start doing some of the same thing with a quadratic function. The big deal is, we got to deal with that h, right? We don't want a third variable. We want x and y's, and that's it. Okay, well, that's where the limit comes in and helps us out. Is there anything clear up, though, with getting to that point for somebody? All right, so we're working on this, and I'm going to transition, then just go back again, and let's say, hey, what if we look at this from the limit definition, and we're combining this, okay? Now, there's going to be some rules that we have to put in place. That's why I'm just kind of doing an intro for today. What's the average rate of change? How do we calculate it? And then don't forget, hey, the limit can join this in a nice way, right? Now, that doesn't mean the work is always going to be easy. As I think we'll have a couple minutes, I'll be able to show one that definitely has a more work involved, okay? But what we're seeing here is when I did all of that, we get to this situation where now I have the limit as h approaches 0. And it was what, 2x plus h minus 3? Now, should we be surprised to see the 2 and the -3 here? Does everyone see the -3 came from the very problem that we had? It was one of the coefficients. Where'd the 2 come from, though? Where was the 2 at? When you look at that, the only 2 we had was an exponent, right? That's definitely things to watch for as we deal with this moving forward, okay? Kind of a hint of things to come. What we see here, though, once I bring this limit in, what term can I now deal with? The nice thing is here through direct substitution, right? I don't have the division anymore. It's simplified out, right? So now I can do direct substitution that says, hey, if h is 0, that term is 0. And then I can say that this equals 2x minus 3. Okay. Now, as I mentioned, we definitely got to get some other terminology and definitions in place because continuity, as I mentioned, is definitely an important one. Okay, that's why working with a quadratic is we familiar with the parabola. Hey, I can have some confidence that it's continuous for all real numbers. Okay, not always the case as we saw some other graphs last week. With stuff like continuity in place, and there's going to be ways that we have to describe the graph to make sure it is differentiable. We'll kind of briefly talk about that. We could have confidence in that this new function will describe the average rate of change at any point I pick. So, for example, what if x equals 3? Well, if I do the whole thing that we did before, I could plug it into this and work it out, and I would get something, right? The h would be left over unless we bring the limit. But with this new expression here, we can do like, hey, 2 times 3 minus 3, which will give us what, 6 minus 3 or 3, right? We could actually evaluate something, okay? And this is where we're going to start to see the differentiation moving into what we're working with, okay? The rates of change is definitely a big focus of our course, okay? Any concerns with this second one going through all that? Okay, and as I mentioned, once I get, the continuity in place, we can talk about that. We're only got about 10 minutes left, so I don't want to try to squeeze it in. We'll better be able to explain why the limit and how to interpret or what we call the 2x minus 3, right? So we'll do that. Now, since we do have a couple more minutes, we can look at another problem real quick. This one you don't necessarily need to copy down. If it comes up, you'll know, okay, this is a situation to watch for. All right. Certain things that we'll run into, and I'll try to spend more time with them when we get to them. It's going to be like logarithms, like I said. Some exponential problems can get kind of messy here, but there is one example we can look at. Okay. So is everyone good with these first two before I go to the last one? All right. So the last one, let's say we have f of x equals the square root of x minus 5 plus 11. Now let's not do that. Just do plus 1. Don't need to make it too much. Okay. All right. The problem here that we run into is because we have a different kind of function we're working with. It does create like a situation like, how do we deal with simplifying something? Okay. What we need to be prepared for is the handle differentiation. As you saw with the quadratic, hey, I can just simplify the expression once I plug in x plus h, do the subtraction, and the terms cancel out. With a radical, we're not necessarily going to be able to do that. Okay. So this is a good example that, hey, when I go in here to do the difference quotient, I have to be prepared to handle it in different ways. So if I'm just looking at the difference quotient like we did before, the one thing we do need to find is f of x plus h, but what you're going to find is there's nothing we can do. We plug it in, and I'm stuck at that point. I can't do anything else with it. Okay. That's all we can do is plug in x plus h. Okay. Now, when we get to the difference quotient, though, make sure you're careful to see I had that plus 1 on the outside. Because there is one term that will end up still canceling out to 0. Which will be your constant term. okay, because it's outside the radical, we'll be able to say like, hey, that's gone. And all I have up there is the two radicals. Oops, got my H. We're okay with that so far? Now, what happens, as I mentioned, though, that leaves these radicals. I've got to find a way to deal with them. Right? Squaring would help, but the problem is we have two terms. Right? So as we saw when we square two terms, that's going to give us a trinomial. Right? And what you're going to find is these two terms will get rid of the radicals, but then you'll have both radicals being multiplied together on one term. So that's not necessarily going to help us all the time. Okay. So how do we create two terms though, using that same kind of idea? How do we get to this here through multiplication where I don't have a middle term? There is one group of factors that allows us to do that. Now I didn't put something there though, because the sign matters a lot. I have two squares here, right? If I make this subtraction, what was the special name we gave this situation? The difference of two squares, right? What are the factors in of this? Because that will be the multiplication we're looking for, right?
A plus B.
A minus B, right? What we call this in this particular case is we want to take a factor and find its conjugate. We have one factor already, right? That's our first factor. What we want to see is both terms get squared. If I can square each individual term, hey, the square roots go away. That's an awesome thing. Okay. Now what happens is these are not exactly the same. So just squaring it is not going to help us, right? So that's why we have to pick something to multiply with. So right now I have subtraction. Well, guess what? If I can introduce this, we're good to go. Now just remember though, when you work with fractions, you can't just multiply by something on one part, right? What you'll find here is, hey, I'm going to multiply by the same thing, but with a plus, right? I just have to remember to do it in the numerator as well as the denominator. You have to do it to both parts. Okay, you can't just do it to one, you have to do it to both. Okay. This is what we call multiplying by the conjugate, right? And ultimately what you see here again is it's not that we're squaring the numerator. What we're trying to do is square each term. That's really our desire there. Okay. Now, is this going to come up all the time, y'all? No, so please keep that in mind. When we get to like defining derivatives, as we're called, when we start differentiating, we'll have rules that help us get through this, okay? This is just us setting up like, what is the math behind getting there, okay? And as I started off with, I warned y'all that this one's definitely a little bit more involved. Hopefully you're looking at that quadratic one like, hey, that was nice compared to this, okay? The nice thing about this multiplication though, you can go FOIL this out if you want. Nothing's wrong with that. But remember, hey, that I chose that because it's a difference of squares, right? So just go in there and say, hey, that's going to give me the first one squared minus the second one squared. In the denominator, just keep it as you had it. Okay, no need to distribute the h. Okay, and the reason you definitely don't want to distribute the h is, remember, we're doing all this work to try to deal with that h. That's a big deal, a big part of that. Okay. With that in place, though, okay, so the square roots are gone now. What you're going to see here, though, that numerator is kind of looking like what we did before now, though. So everyone see that kind of similar to what we had before? It's definitely more going on because we still have all that in the denominator, but the numerator at least looks a little bit nicer. So what we're going to be able to do here, though, is just distribute that negative, and the x and 5 are gone. Everyone agreement there that the x and 5 would be gone? Which leaves us with what in the numerator?
H.
Just the h, right? Now, the reason we like this here is because now we could divide out these H's. Everyone see where simplifying the numerator gives us the H's. Now we can divide it out. Which remember before, that was what we wanted to happen, was the H's to divide out, okay? But it took some simplification to get there, right? That's where your algebra skills come in to build up to this, okay? Now, please keep in mind, this would definitely not be one I put on the test. Is everyone okay? Understand that? This would not be a test problem, because it's great to know how to do that. And if you were in, say, Calc 1, right, the science major side of things, I would expect that, like, hey, we should be able to work through this because the algebra is very important. But for our class, what I want you to take away from this is, hey, this is what defines what we need moving forward. This is important, right? It helps set the foundation, but we really want to get to where we're trying to get to. Does everyone understand that? Now, what you find here is the nice thing about this one, it gives us 1 over, oops, the square root of these things. But the nice thing that we get from there is now you could, if you wanted to, you could go in and say, hey, this is just 0 using the limit. I don't have to worry about dividing by 0 anymore. But what you're going to find there is both those radicals are going to be the same thing, right? So you'd be like, hey, I got 2. Okay. But I'll make sure to kind of point that back whenever we get to the rules of derivatives and stuff. I'll make sure to point back to this to show you, like, look at all the steps we save by just making sure we know the rules. Everyone follow that? Because we will deal with this function when it comes to differentiation. We just don't want to go through this process. We okay with that? Everyone understand at least the whole conjugate idea? That's definitely an important thing to review. Difference of squares. Any questions or concerns as we finish up? All right, so just keep in mind, right, we're building towards something. If you get stuck on any of the limit stuff, please just reach out to me, okay? I definitely could have a conversation, but I feel that would be better one-on-one in my office than taking up class time, okay? The other thing is, if I know a couple of you weren't here when we started class, make sure you come see me for the attendance, but also know that Friday right now, we're gonna have to do a Zoom session. It might only be a few minutes, right? I'm thinking 30 minutes Friday because of a doctor's appointment that got bumped back from last week. It wouldn't have messed with my classes, but with the snow, it got messed up. So the only available for like a whole month was that Friday. Okay, so please keep that in mind. And if it changes, I'll make sure to update you. I'll post an announcement to confirm it or let you know if something changes. How about that? Have a good day though, and I will see you all Wednesday.